Peter Breen, and David Flint. And our advisor is Steve Sager. Just to give a quick recap of the project, basically we're building a machine to cut mechanic sockets to accept a radio frequency identification tag in order to know where all of your tools are at all times and to reduce foreign object damage in the aerospace industry.
So recap our cutting procedure. We developed a two-pass technique. This allows a roughing surface to remain on the socket. This allows extrusion of the oxy for the RFID tags. So our pass one is a spindle speed of 2,500 RPM with a travel speed of 20 inches per minute. The depth of cut 55,000. This is the primary cut. The secondary pass is what actually makes the roughing finish. And the same spindle speed with a travel of 100 inches per minute at 5,000 depth of cut. As you can see by the picture in the middle from the optical comparator, are the scratches that are made for the epoxy adheres to.
Just a recap of the machine design, we decided to extensively modify the central machinery mini vertical milling machine. It met our performance standards when we tested it at HABCO, so we decided that this would be a viable option for the spindle. And we're going to automate it with PLC components donated by Automation Direct, which is now our secondary sponsor. A final part assembly of our machine. This is a little bit different from last time as we made some minor adjustments to this bracket in order to get a little more clearance. We also finished the complete layout of where the spindle was going to be in relation to the base plate, and you'll see in the back that we changed the motor bracket a bit. So if you remember from last time, the motor bracket was slightly more angled forward. When we went to order the belt for our drive, we were limited by the size that we can use, so we had to change the angle of the bracket in order to not allow the bracket itself to be pushed off the edge of the table. We're going to talk about manufacturing parts. Most of our all of our manufacturing was done at UCONN, and some of it was done in Castleman Machine Shop. It was done on the Haas VF2 CNC or a Bridgeport milling machine, but most of it was actually done at the Formula SAE shop on our Dynapath CNC mill and our Kent vertical mill. We also used our HTP invert TIG welder. All of our CNC was programmed using Mastercam. You see on the screen here, it's just a snapshot of one of the parts that was being made, and there's our Dynapath, and there's our vertical mill. On the top left here, this is just a brief layout of how the assembly of the machine was going to be on our base plate. This is the socket stop, this is the sliding block, this is the base of the machine, and then the actual base plate. To the right, we have the base plate fixtured on the mill. We're drilling holes to fix the machine base to it. Over here, we just have a picture of the CNC mill. We're about to machine one of the brackets. And then on the bottom right, we have the semi-completed assembly of the machine itself, including the spring-assisted cylinder, the D-block, and the base plate. Everything's bolted on it.
While we're manufacturing the machine, we're also obviously automating the machine, and so this is just a quick recap of what we went over last time. Basically, we're using electrical and pneumatic controls. It's consolidated into one box, which you'll see in future slides. And there's 3 basic controls. There's a start button, an emergency stop, and a find home button. This is the basic procedure of after you start, what the machine will do after that. I went over last presentation, so I won't go over that again. But now moving on to schematics.
So we saw last time we had a brief line layout with schematic. This is an official schematic. We worked with HABCO to make it 100% accurate. So as you can see on the left, shop air comes in, 100 psi. Goes through regulator and filter assembly down to 50 psi. Goes through an oiler so that everything can maintain proper working order. Goes through a T-fitting. In the top part, it goes to the clamp for the actual D-block. So it goes through a solenoid and a flow control valve. The flow control valve ensures that the air cylinder don't slam closed, so less wear and tear on the machine. And then, of course, the air cylinder. The lower part of the T-fitting, same thing, the double acting solenoid this time. Same thing, flow controls, we don't want anything slamming open or slamming closed. And our double actuated air cylinder, which will control the depth of cut change on the machine. So the pneumatic layout, all the components that were on that schematic you can see now, it's on the side of our electrical enclosure. So we have our regulator, filter, our oiler, and our solenoids, which control the flow there. Same thing with electrical schematic. You guys saw a line drawing last time. Again, we're going to have to make an actual official schematic. It's a little tough to read in the projector, but I'll just go through it really quick. On the left, you have 120 single-phase power coming in, standard three-prong plug you plug into the wall. Comes down to a DC power supply that powers our PLC, powers some other components of our machine. Goes to a transformer, which converts to three-phase power, which is needed for this servo motor. Bottom left is our servo drive. This controls all movements of the servo. In the middle are our add-ons for the PLC. The add-ons are outputs, because we ran out of outputs for the PLC. Luckily, with the click PLC we're using, they basically click on the name of the device. And so we have additional outputs. On the right is our actual PLC with inputs and then some additional outputs on the bottom. As far as the inputs go, they include switches and home button and all that. We put a lot of thought into the switches because switches can be either normally open or normally closed. For an example, for our emergency stop switch, we decided to make it normally closed. That way, if there's a failure in the wire or in the button, the machine will stop. Whereas normally it goes a normally open switch and say a wire failed, the machine would not know that the switch did not work. So this way, if something's broken, the machine just will not run.
You know, that's a picture like that, which you're right, nobody can read it. So it'd be good just to annotate. There's a couple of things you're talking through, just to make it more effective. But keep going.
So same as the pneumatics, you saw the schematic, now here's actual physical components. In the bottom of our enclosure is the back plate, and everything is mounted to the back plate. I'll explain it in the next slide. But as far as this slide goes, this is our user control, very simple controls. We have the start switch, home switch just finds the home position. Our running light is a yellow light, our red light is a halt light. It's triggered if the machine starts to over travel or the emergency stop is triggered, you can also emergency stop. Moving on to the electrical enclosure. Same thing as before, so this time it has all the electronics inside of it. On the left inside the door is the control for our mill. This is the original equipment that came with the mill. We didn't want to mess with it. The electronics work. We're using the stock speed in the mill, so we just attached it without messing with it. On the inside, in the top left, is our servo drive. That's the biggest component inside there. It took up a lot of space, basically dictated the size of our box. In the top is a 50-pin rail that helps control the power coming out of the servo drive. In the middle is our PLC with DC power supply and add-ons. Bottom left is our transformer, converts to three-phase power. Our fuses, which we checked out from the machine, and our contactors, which are basically relays.
While obviously doing the schematics, we actually have to automate our machine using code. And so we're using a click software code, we're using a click PLC. And just to go through our code a little bit, basically this first page of our code describes how we find home by both pressing the home button and by pressing the start button, because we want it always to start at home. Next, after it finds home, this next part actually activates the solenoid to close, turns the spindle on, and enables the servo to actually initiate a command, so it will be to position 0. And as you can see, in order for it to actually move, it needs the command function. And we put a wait time in there, so it can actually have the spindle start up and have the pneumatic field devices actually close completely. After it reaches position 0 or end of pass 1, it needs to push the cutting deck forward to a full 60 thousandths of a depth and initiate the secondary position or position 1. And as you see on the next slide, we also put in another time delay so that the command function would be 1 second later, and so the table can fully push forward. After that, it will reach home again, because that's the position back to the home position, and therefore the user needs to remove the socket, and so therefore reinitiate a device to open and the spindle to turn off, and everything's done. And so then lastly, we added in some code about the emergency stop and the over travel limit switch, so that everything will shut down just in case of an emergency. No trigger a fault light and stop the machine.
Well, the same comment, only annotation, right?
Yes, exactly.
Yeah, 'cause you said, and you can see, well, I don't think anybody can see, right? So you need to just annotate a couple of the key points, that's all. Keep going.
Absolutely.
So moving forward, most of our manufacturing is complete. With the exception, the cutting deck is complete. We need to cut the base with a spindle, which is just 2 simple dovetail cuts. We need to weld the motor mount, take a couple hours. PLC code is complete as of last week. Our electrical assembly is complete as of this week. And run pneumatic lines, only 3 lines to run, very simple.
In our risk assessment, we have mistake machining up there. Although it's going to be rare, it would be catastrophic if it happened. We'll talk about the mitigation in the next slide, but we gave that a 5. If we break the machine, crash while running, that's pretty significant. We gave that a 16. It would be a major problem, and it's likely that that it actually happens because PLC code never works the first time. So that will happen. The failure on demo day would be catastrophic, but is unlikely considering we were going to be testing a bit. And PLC code errors, we gave that almost certain likelihood, but a minor impact because nobody's code ever works the first time. And then, so to mitigate these risks, mistakes machining, basically we adopted the measure twice, cut once principle, so that we double check everything before we cut it, because we only have limited resources, limited time, to make sure everything's right the first time. Mitigate the risk of breaking the machine, we instituted Delrin shear pins and had the servo. We're going to use a servo function that is over torque value, so we're going to set a value on the servo drive, and if the machine reads a certain torque over that value, it's going to stop the machine from running. And we're also going to run the machine with no end mill and no socket in there to make sure that nothing crashes into the tables and whatnot. Failure on demo day, we're going to avoid this by validating the machine, just running it consistently, trying all kinds of different ways to trick it or break it or just test all the functionality of the machine. And then PLC error codes, actually, to mitigate this, we're going to go to HABCO today and start testing our components. We're going to plug in components by themselves and put a couple of them together and just basically start by pressing the buttons and seeing how things work. Touch the limit switches to see if the machine stops and faults and debug the code.
So you're kind of a systematic test program that you want to run through to understand.
Right, we're basically going to start by just plugging the parts in, not attached to any parts of the machine, and start running through the code and checking through things to make sure that the field devices and the inputs are functioning properly.
I think you stop in the middle of travel, checking if the limit switch is hit, if we can still find home after then.
Okay, guys, use your clickers, please. Comments, questions?
Do you guys look at any OSHA regulations? For example, say like I'm operating the machine, I press go, and maybe like it starts cranking down the socket and the socket falls and I try to quickly push it back up. Like, is there any, I'll see like maybe like a 2-hand trying to switch just so you can't drop your fingers.
Well, we had originally considered a 2-hand switch back last semester when we were designing the machine, and we determined that the machine wasn't going to be used enough. That it's not going to be used 24/7. It's only for, say, we get a socket cut here and there, then we'll cut it. We're going to have a guard in place while the machine's running, and also emergency stop. So it's very similar to standard bill.
When you're debugging today, you're mostly checking out the logic of the PLC or electrical connection?
We'll find the electrical problem, but we're checking the logic.
Other questions or comments?
You checked your electrical circuit yet? Because you're going from 120 in, and then you need 24 volts in one spot, you need 3-phase in another spot. If you could pull that off first shot, I'd be very impressed.
So we spent probably 10 or 15 hours total just working electrical schematic. We had about 3 5-hour meetings with Pete over there, who's a senior electrical engineer. So the schematic is actually an official schematic, it's done properly. And the machine was wired professionally too.
Okay.
So we're not overly concerned. Of course, there's always, chances for problems.
That's why it looks so clean, because
Yeah.
you guys didn't do it.
No, they actually did. They did most of it. I cleaned up the final schematic, but I made sure that they were putting the input forward.
I'm impressed.
Is it your intent to have it running on demo day?
Absolutely.
You may not. I don't think you're not going to cut a socket, right?
Absolutely.
Oh, you are. Okay.
Oh, yeah.
That'd be good. That'd be cool. That'd be very cool. That'd be very good. So, yeah, I think you guys have done a very nice job here. I think what you want to think about in not only your final report with all the documentation you need to provide HABCO, what you're going to actually present on demo day besides just the machine. There's going to be some schematics or something like that. Those ones are that. Some of your original work on defining machining parameters for the roughness was a good piece of work, so you might wanna, make sure you summarize that and be able to speak to that if somebody comes through and if that's right, so, okay, very good. All right, nice job, guys.